so much for coming to our Building Flexible Thinking in Mathematics webinar today. Just some webinar logistics to start out with. We want to thank the New Hampshire Department of Education. They are sponsoring all of these webinars so that we are able to give you them for free, and they are committed to getting all of the word out on a lot of these topics and some that we've already had with modular assessments and data. Everything sort of data related is been able to come to you for free. So we appreciate our partnership with them. Just so you know, also, everyone is muted. We cannot hear you. We do want you to ask questions. If you could enter them into the Q&A section of your Zoom screen, that seems to work the best, especially in a large webinar format like this. It's really hard to have you raise your hands and for us to unmute folks as we're going through the presentation. We might have some time at the end. If some folks stay on, they can maybe raise hands at the end, but it's always good to have your questions as we're going through the content so we know exactly how to answer your questions. So in that Q&A section would be great. A lot of questions that we get is, are you going to get a copy of this specific recording for this webinar and the PD certificate? And yes, you will. An email will go out tomorrow with all of the information. There's a couple of materials, some, supplemental materials that will be in that folder, as well as the PowerPoint or Google Slides for this. At the end of this, there will be a brief survey. I always say Annie and I look at the feedback that we get, and it is true. We look at it and we try to do everything we can to make any of the webinars that we're doing better. And we would appreciate if you would just take just a couple of minutes. I think it's a 4-question survey. This is who we have today. I'm Heather Jenkins. We also have Annie Wallace here from the New Hampshire Department of Education.
Hi, everybody. Thank you for coming.
All right, get started. So it's easier for you to see your screen. We tend to turn our cameras off. It makes your screen hopefully just a little bit bigger and we don't take up any of that space. So this first section here. So our agenda, we're going to go over just the general understanding of what flexible thinking in a mathematics classroom is. Then we're going to talk about some of the problems, tasks, and how you facilitate discussion. We are also going to talk about how you're going to transfer this to the classroom. And again, we will have some wrap up and question and answer at the end if there's still some things that are unanswered for you. So why build flexible thinking in the classroom?
Often when we're asked to say or think about what a classroom looks like, we think about students sitting in desk rows, paying attention, taking notes as the teacher lectures, following the procedure for the type of problem the teacher shows them and tells them what to do. This is step 1, this is step 2, this is step 3. So when we see the example of a traditional math lesson, it's I do, the teacher shows the kids, the students, here's what we do, you do this step, and then they do some problems following what the teacher does, and then they try it on their own. But often, not always, but often the I do, we do, you do approach can often lead to what Peter Lilladell calls mimicking, or the students fake knowing what they can do, or they're not paying attention and trying to do something else, or they stall it or say they tried it. So students do a lot of activities, but not necessarily a lot of thinking. So they can be taking notes, answering questions, filling in worksheets, and playing math games. So Peter Lilladell in his book, Building Thinking Math Classrooms in Mathematics, stated that in a typical 1-hour lesson, 75 to 85% of the students were exhibiting non-thinking behaviors for 100% of the time. and the rest of the students exhibited non-thinking behaviors for all but 8 to 10 minutes of the time. So most of the time, they're not really thinking. They're following what they were told to do. They are trying to remember the procedure and do the procedure, but they're not making the connections and the relationships within the problem. So how do we get students thinking? We want them to be engaged in their learning. We want them applying their knowledge and thinking about their knowledge that they have in solving what they're learning now. So through flexible thinking, using problems and tasks with a high level of cognitive demand can help get students engaged, help them to stop and think about what they know and what they're doing and how they can approach the problem for them. So how much of how classrooms look and what happens in them is guided by our societal institutional norms. And most of these really haven't changed since the late 1800s, early 1900s of the industrialized age model of public education.
Right. So we have this sort of thought or this question of, do we want kids just memorizing or mimicking math procedures, or do we want the kids actually learning and doing or applying math, right? So I think we all know we really want kids learning and doing and applying math. So to be able to learn math, we have to be able to think math, right? We have to be able to think about it. We have to be able to discuss it and be provided with opportunities and tasks that engage that thinking for mathematics. So again, we're back to this example of a traditional math lesson in maybe second grade. This example we're using too, I used this method when I taught second grade a lot. And it's basically looking at the traditional algorithm here and really starting to think about, as you're going through your teaching, let's look, this is a standard here. I can fluently add and subtract within 100 using my understanding of place value and the properties of addition and subtraction. A lot of the ways that this particular standard is thought, or your interpretation of it is, at least mine was, is that if we're talking about place value and addition and subtraction, we line it up. But in fact, that is not the case. So if you look at the learning progressions for grades K to 5, a lot of what they're looking at for even addition, subtraction, multiplication, and division is understanding that first counting and cardinality, right? Understanding what it is and what contributes to the understanding of addition, subtraction, multiplication, and division. All right. So we look at all different methods to be able to do those types of computation, right? That does not necessarily mean that we right away are giving students the strategy of using the traditional algorithm. It's difficult not to, because specifically in their homes, if students, are working with parents, that's how we learned traditional algorithm. It was a rote understanding. This is what I do. Here's a procedure that I follow. But if you look at the learning progressions here, you're looking for the words traditional or standard algorithm in the specific standards. You can see that there are no standard algorithms or traditional algorithms anywhere in the standards at all until 4th grade. So we want to be careful of using just the traditional algorithm as a standard way to be able to teach addition and subtraction. We want to think about different ways in which we can teach it, with breaking numbers apart, how numbers are really related to one another, having kids use different strategies to be able to solve the problems. If they use different strategies earlier on, they're building those math concepts that they really need to have to be able to understand how to use the traditional algorithm and to be able to use that particular way of solving a problem as well. Just a reminder for folks for the math standards. First of all, we want to know our standards. Those are the progressions that I just showed you. But the Achieve the Core is a website for some of you who may not know. It is folks that are really well versed in the Common Core. they have created a set of skills for each grade level. It's an algebra progression, but it tells you what your major, supporting, and additional standards are in each grade level, so that you know in your grade level what are the most important standards to be teaching for mathematics and what are the deal breakers for mathematics. On that website as well, there is this coherence map. And what this does is it allows you to see if you're working on a particular standard, what were those prerequisite skills to be able to get to those standards? So if your students aren't really understanding it yet, and also where those skills are actually going or what's coming next for that. This can also help you understand if you are actually teaching to the standard for your grade level, or if you might be misinterpreting it and doing something that they're not quite ready for yet, which is in an upper grade. The New Hampshire Department of Education also has the progression documents for each domain of math. You can see at each grade level what students are asked to do and what those standards are within that particular domain and how they build off one another. I'm just going to pause there and just wait just a second to see if anybody has just any general questions about what we were talking about when we're talking about flexible thinking in math.
Right now, I'm not seeing any questions.
Okay. Again, put them in the Q&A if you have any, and we will be sure to stop and try to answer anything that we can. So the next portion of this is we're going to start talking about problems, tasks, and facilitating discussion in your classroom and how you can start really building that thinking classroom. So using the problems, tasks, and discussion to support flexible thinking.
So we want to make sure that we're thinking through problem solving, or problem solving does provide a good background and foundation to build that thinking off of. So we want to develop a problem solving classroom. However, there's some misconceptions in approaching problem solving that can lead to difficulties. So especially in developing those problem solving skills, and these in turn then affect the learning. So oftentimes problem solving is often taught in conjunction with the mnemonics and memorized procedures that aren't always predictable, or if you go from area to area, they change, but they take the focus away from the literacy and mathematics of the task and focus on, again, going back to a procedure to follow. Sometimes problems chosen are often too routine or familiar for students, so they're not pushed a little bit out of their comfort zone, saying, what do I know? How can I apply it to solve this? And sometimes problem structures don't vary enough. They see the same type of problem over and over and over again. And it could be something as simple as the triangles are always drawn in the same spatial configuration. It's always something added to something equals something else, rather. And so just changing up a little bit, like something equals something plus something, just that change in the configuration of how the equation is seen can cause students to stop and think a little bit. And instruction seldom includes reflecting and writing about the mathematical practices and procedures and processes used to solve. So just stopping and asking students, how did you get that? Why did you try that method? Is there another way you can try it? It just helps them to think. And you can see thinking through problem solving involves a whole lot in the classroom. You're talking about things, you're doing assessments of problem solving, you're facilitating discussions, you're also looking at the skills. What are technology and resources you need? What is the problem's purpose? Oftentimes we just give a problem because it's there in the textbook, rather than thinking about what will my students get out of the problem? What can I see about my students' understanding if I give this problem? So there's a whole lot to think about. And then it's the type of cognitive demand and problems that we also have to think about. So they're playing memorization tasks. They're just following the procedure, going step by step, but not really understanding why each step is done. It's often like the Thanksgiving story you hear where somebody says, they're asked, why do you always put tinfoil over the turkey? And it was because my mother did it. They don't know why. It's always been done, so I do it that way. And then there are procedures without connection tasks. So we want to make sure that students are building that understanding of the procedures. So by the time they're in fourth grade and they really start working and solidifying the traditional algorithm in addition and subtraction, all those previous years, they've really built up a strong understanding of place value and how place value plays into the efficiency of the standard algorithm. So while we may use those two low cognitive demands to get people started, we want to make sure that we're really pulling in the procedures and building the connections to understandings and concepts in the procedures, as well as actually applying and doing the mathematics.
Okay, so here is, why would we do this, right? How are we doing this? So the reason we do it really is to support the development of mathematical practices. So we have our standards that we need to be able to cover in every grade level. We know what those are. If students aren't getting those particular skills yet, we can go backwards and we can say, okay, what were the prerequisite skills that these students had, and do maybe some reteaching or a little bit of understanding of, okay, what do we need to be able to get here? When we talk about using some open-ended problems, which we'll get into as well, that's another good way to be able to differentiate and try to figure out if students aren't quite there yet. Maybe there's a different entry point for a specific problem to be able to get the students who might not quite be there yet to be able to also access some of the problems that you're doing in your classroom. So we know all about the standards, but one thing I find that people forget about are those mathematical practice standards, those perseverance, the reasoning, the modeling that needs to be done to be able to really, truly understand what math means in the classroom. So we want to really be able to support the development of those practices as well, right? The question is, right, we want those tasks to be able to have multiple strategies to be able to solve them, or multiple methods. That's where the thinking and the understanding comes in, right? If there's only one way to solve a problem, then it becomes something that kids won't have that flexible thinking. Or if we only show one way to solve a problem, it will create this sort of, narrow line for them to be able to follow, to be able to have that creative problem solving when things start to get harder, or when they have, a novel situation in which they need to be able to apply these skills in. And then this last piece here is that you can open up current problems and tasks to allow for higher cognitive demands. So we're going to talk about some of the things that you can do to be able to open up problems and to be able to not have it just be this plus this equals this.
Before you go on, we do have a question. I think that's a nice thing to go between the two sides is, what happens when students do not have standards from prior grade levels and it seems like there's a lot of remediation rather than moving ahead? Do I just move ahead?
Right. I mean, that's where the balance sort of comes in, right? We know that this is the way students are coming into our classroom in a lot of cases, is they're coming in a little bit lower than where they were before. But while you need to be able to ensure that they have those prerequisite skills, and there's a lot of different ways you can do that. We have some webinars coming up on differentiation that isn't just differentiation, meaning I'm creating different activities for everybody, but differentiation in your questioning, the way that you're presenting problems. Those are all ways that you're going to be able to scaffold those particular skills and to be able to get kids where they need to be. The biggest thing that I would say is also you need to make sure you keep your eye on the prize of what your particular standards are in your grade level and not just continue to lower the bar to meet where the students are at, or they'll never catch up. I don't know if you have anything to add to that, Annie. Or any
No,
other
and
thoughts?
I think hopefully, as we move on, people will see how they can open up and problems so students can enter where they're at. And if anybody wants to email me, I can send them a document that has some of the supporting standards in the grade levels before their previous standards to help them with scaffolding of problems.
Great. Sounds great.
And then we just have another, sorry to interrupt, another problem about what are your thoughts about fluency, math facts? Should you be able to be quickly and accurately know multiplication and addition facts? And yes, you need to do so, but not through just plain memorization. You have to help teach students strategies to do that. And when I have time, I'll try and put in the chat if I can access it, or you can email me. We have some videos with Professor Sharma who helps show how some of the strategies that you can use to develop that math fluency and understanding of the facts.
Great. Thanks, Annie.
You're welcome.
All right. So when we're talking about setting up tasks, a lot of times when we're teaching, we have specific programs that we're using. So the tasks, we just put them up as they appear in our curricular materials. Every once in a while, we as teachers set up tasks ourselves. I've noticed a lot recently, anybody who I've worked with in the last few months, it's a lot, these tasks set up by teachers. The big discussion that we're having too around education is the amount that we talk as teachers and not giving space for students to be able to have those discussions themselves and to be able to really sort of deepen their thinking. So we set up the tasks as teachers as well. So sometimes we have something in our curricular materials and then we set them up on our own, or we look and we're looking out at our class and it doesn't seem like they're getting it. So we put another problem up and another problem up. Well, that's all well and good, but we also know that the tasks that are really enacted and talked about with teachers and students, and they're really working through them together and understanding all the different ways and the strategies to be able to solve problems, is where student learning takes place. So it's not necessarily the number of problems that you're doing that is going to really deepen that thinking, but it's the ability for students to be able to think about it, to discuss it and talk about it that will really have those students deepening their understanding. So on the bottom here, we do want problems and tasks to create purposeful discussions. We want them to be able to think about their ideas and develop their understanding and reason with others. So sometimes we can start even with a low level problem and do that, or we could start with a higher level problem and do the same thing. So some of the other sort of help that you can do is you're looking at specific tasks that you might be doing in your classroom. This is just a sort of general checklist to be able to say, if you are doing specific tasks in your classroom, here are some of the questions about like the task potential. Is it, is there anything problematic about the task? Is there anything interesting about it, right? Are there goals that are, that you have for your students in your classroom? Do they actually align with the task that you're doing? What sort of strategy, you have to kind of think ahead, what sort of strategies might students use to be able to solve these particular problems? And are there any misconceptions that might be had if you're using this particular task? When it comes to problem solving strategies, we want to make sure that we're having students use more than one strategy. So these are just different strategies that students might be able to use as they are completing tasks in your classroom. And then what features do the task have? Is it high cognitive demand? Are there multiple entry and exit points? This is what we're talking about when we have students. If we have an open problem, if we're talking early elementary and you say, give me 2 numbers that might add up to 10, right? There's a lot of different answers for that, right? So we could do a problem that is exactly that. Give me 2 numbers that add up to 10. But then maybe if you have a higher student, you might say, what are the 2 highest numbers that we can have that add up to 10, right? Like, or which numbers do we have? What's a double that adds to 10 or whatever it is? You can just start talking about just multiple entry and exit points for them. And then for assessment, we want to make sure that we are having students use tools and models to represent math. They're not just doing rote learning. They have reflection, they might have explanation. There's multiple ways that they might be able to demonstrate understanding there. So this is just a graphic that's showing us, so we have students that have procedural fluency, right? That is that, okay, this is how we do it. Here's how you complete this particular activity. And they have that, and they might even have that conceptual understanding. You want both of those, right? So you need that conceptual understanding, not just the procedural fluency, but the 2 of them together are equal to your mathematical proficiency for students. I really like this diagram here. This is, I think, a perfect example of having flexible thinking and a real true conceptual understanding in mathematics. So this is basically relational understanding of a math concept. So you've got ratio of 3 to 4. For a lot of students, they might stay in this, 3 to 4 or 3/4 or 3 to 4. This whole area here might be what they're really kind of visualizing and stuck in. But you can see all these different ways in which students can conceptualize the ratio of 3 to 4, right? So there's a lot of different ways that we're representing our thinking, a lot of different ways that we are showing our understanding. And a web like this is just really indicative of having students start sort of pushing their thinking to another level. This is another graphic that we have where we're looking at procedural fluency and developing those conceptual understandings. And really, it's about making those connections, right? So you have your procedural fluency, you have your procedural knowledge and understanding underneath that. You know what's going on, you know how to be able to solve problems, but underneath that, you have that flexibility. You have that, for some students, efficiency. They want to, solve it in a completely efficient way. Obviously, accuracy is big, but there are many times that I have said in my classroom, I'm not really worried, and it's not that I don't care, but I don't care what your answer is today. My big thing that I want you to think about, and really what we're working on today, are the strategies that you're using to solve this particular problem. Right? Because if they have the strategies, then the accuracy will start being there. So we're not hyper focused on accuracy, we're hyper focused on procedure and what sort of, strategies are you using to be able to solve this problem, right? So that's that appropriate strategy selection here as well. And really, the whole point of this is that procedural knowledge is really based on that conceptual understanding. They have to have the conceptual understanding to be able to do this.
So knowledge is not tiny bits that we can count and represent by numbers, but really it's a network of logically interconnected ideas, beliefs, and generalizations, structured so it can be searched and used to work out and evaluate new ideas. So that's basically what problem solving is. We want to take what we know and think about how we can apply it. And as we do that, we start learning new things and making new connections and seeing new relationships. So how can we use tasks to open up opportunities to help make those connections between concepts and procedures? So here's the simplest way is to start scripting some of the basic problems you have. So a basic textbook worksheet pay thing could be 3 1/10 plus 5 2/10. So a simple method of starting to get students to think and think about the knowledge they have is just by asking some simple questions. So begin with a review of prior learnings. What two whole numbers would the answer be in between? So they have to think, if I'm rounding, 3 1/10 is close to what? 5 2/10 is close enough. So what's 3 plus 5 or 4 plus 6? And say my answer should be between 8 and 10. So it's getting them to think about things and to pull on what they know. And then another simple way you can do is just ask an extension question. So I have 3 1/10 and 5 2/10. What could be a question or a story for this problem? So they're fitting the numbers into context. And then there are some simple strategies that go beyond just scripting to help open up problems, modifying questions, problems, and tasks. And many of these are from Barbara Dougherty, who was a professor at the University of Missouri and then at the University of Hawaii, but she's done a lot of work with elementary school teaching and extended that into the middle school and high school. And how can we open up problems to include access for all students? So the first one is generalization. So if I'm given my typical textbook problems, worksheet problems, here I am just adding numbers. So the generalized version would be find two two-digit numbers whose sum has 3 digits. What's the maximum number of digits you could get if you added 2 3-digit numbers? What would be the minimum number? And then you have to support your answer. Another way to generalize the problem would be, Renee said I used estimation to predict the product of 2 two-digit numbers. My estimate is 400. What 2 numbers could Renee be multiplying? So even though you have students with a range of understandings and prerequisite skills, this opens up the problem so they can use what each student can use what they have to try and answer these questions. So why do we want to use generalization problems? Well, first, it focuses on the big ideas and then pulls together all the smaller skills that they know. It helps students to think and create connections and form a more cohesive mental representation of what they're working with. And it's helping them to think about and find and describe patterns, as well as giving support to ideas that can be generalized to other contexts. Then can you go back one, Heather? Then we have reversing the focus. So I'm given adding 2 two-digit numbers. So rather than just the simple numerical problem that I have, I can ask students, find 2 two-digit numbers whose sum is 125. Find another pair, find 3 more pairs. So it's not discounting the typical textbook worksheet problem. It's just they may have some practice with their adding skills but then you're asking them to go further and to think about the relationships and think about what they're doing by reversing the focus. So, or find an equation whose solution is -12. Find another equation with variables on both sides of the equal sign whose solution is -12. So what I can do in the elementary school, I can take this same idea and apply it to middle and high school problems. So why do we want to use the reversibility questions? Well, it helps us to start thinking in different ways. It helps reverse the train of thought of giving answers and students create the problem. So it's kind of like Jeopardy. You have the answer, now you come up with the problem for it. Holistic, going beyond breaking needed skills into small steps, and it allows for thinking about the process, not just following the mechanical step to get to the answer. Then we have flexibility questions. So again, I can take my typical textbook, just plain numerical problems, and then start open up the thinking about them. How are these problems alike? How are they different? Can you add the numbers in a different way? Solve, here are 3 equations. How are these problems alike? How are the problems different? So you're getting them to start looking at the structure of problems and thinking about what goes in. So why do we want flexibility questions? Well, they ask students to solve a problem multiple ways. So they're getting away from just the imitation and mimicking. Ask students to use what they know about one problem to solve another, and have students compare. How are things alike? How are they different? And finally, they really can help students to start seeing the structure. Using errors or points of confusion. So Illinois had at one point given a model curriculum where they used a courtroom, and they had the mathematical Supreme Court justice, and cases were presented to them. So then students had to say who was right, who was wrong, or were they both partially right, and then why. Phillips Exeter Academy, in their problems, will often have somebody thinking about some errors, and students have to find the error and explain why. I know when I was in the classroom, I would purposely make mistakes on the board, and then the students would, raise their hand all excited saying, oh, you made a mistake, and this is the mistake you made. And then they'd show me how to correct it. Or another way is putting a problem up in the board and asking students, what do you think some common mistakes other students would make in solving this? So that gets them thinking a little bit differently also. And then using equivalency. Why is this equation equivalent to that equation? Why is this whole number divided by the fraction equivalent to the multiplication problem of the same number, but multiplied by the multiplicative inverse, and explain. And then getting students to quickly look at problems and see which ones may be equivalent, and then be able to tell why, or you lead a class discussion on why these are equivalent and why these other ones are equivalent. So why do we want equivalency in errors or points of confusion? It helps to make connections among problems, representation, and larger mathematical concepts. It really helps students to start thinking about the underlying mathematical structure and allowing the development of decomposition and combining, building that flexibility in their thinking. It really helps to differentiate between conceptual errors and procedural errors. Oftentimes, a student knows what to do, they just made a computation error. So thinking about, oh, I know what to do, I have to go back and re-add this. And it gets them thinking beyond just following the procedure. And when they start discussing how they solve problems, they start understanding the reasoning of others, as well as getting them to recognize common errors and misunderstandings. So as they're doing their own work, they're aware of where problems may arise. And then we have multiple representations. These are more middle school, high school equations where, I have a linear function and I can express it as an equation, a table, a graph, and then some questions about the 3 forms to getting them. But elementary school teachers can do with decomposition and recomposition of numbers, just changing what's on what side of the equal sign can help them recognize different things. So it's recognizing that numbers and how you communicate numbers in situations mathematically can vary. So why multiple representation? Well, it helps understand the connectedness of multiple representations. I know when I first started teaching Algebra 1, and then you taught the slope-intercept form of the equation, and then you taught the table of values, and then you taught the graph, and the students weren't making the connection. So building an understanding of all those representations together helps students build the connectedness between the multiple representations of the same situation that you were giving them. It can also allow different entry points for students so that they're entering where they're most comfortable at, and then they're making the connections to the other forms, as well as building an understanding of the structure of what you're working with and connections between the procedure and the concept. And all of this is building that thinking, helping to raise that cognitive demand.
Okay, we'll pause there for just a minute to see if there's any questions. I do see one question in the Q&A, and it talks about it's allowing kids to try multiple strategies that that they're learning, but are only allowed to use one method on the summative assessments. I guess I would just need a little bit more clarification on that, because I know that, with the summative assessments and even the modular assessments, I haven't ever really thought about it as you can only use one strategy to be able to figure out a problem. There are oftentimes, if there's more, there might be an exemplar answer for a specific, whatever you're putting in there for an open-ended particular question, but there are also other accepted answers for those particular types of questions. Annie, do you have anything else to add about that?
I think the more strategies and connections that students have so they can build off of things and then be able to explain why they chose that way helps them do mathematics and solve problems in the long run. Was there a purpose for just choosing one way? I don't know. I think you would have to look at why they're asking this and then discuss among your school
Right. It looks
other
like
teachers and things. Yeah.
it looks like there's a just another sort of elaborated on that. She said, for example, use the area model to solve multi-digit multiplication, but on the summative, only one standard, only use the standard algorithm.
I don't know, and I don't know what your school or district allows in terms of how much can you change the what's expected on the summative only. If you can see they can do the area model, but they haven't quite gotten and made that connection to the standard algorithm, that at least gives you as the teacher information that you have to help the students see how the area model can support knowing the place value and why you may carry a digit over from the ones place to the tens place or the tens place to the hundreds place, and use that to build their understanding of the standard algorithm.
Okay, thank you. All right, so transferring flexible math thinking to the classroom. So here's what we're talking about with teaching concepts and procedures through problem solving, right? We're talking about just even what Annie was just talking about with helping students go beyond acquiring isolated ideas and really help them develop those connections that are needed so that as the tasks get more complex and as you go through the years, you have those all of your sort of prerequisite things that you're really needing to be able to then do more complex math. You have that understanding already built in multiple ways, right? It is not just a single way. So the only way I'm able to solve this problem is to do it this way. Now I have a novel situation and I don't know how to apply it because it doesn't look like what I've done before. So we really are trying to make a lot of those connections to be able to make sure that their understanding is deep enough to be able to create a little bit more and to be able to solve more complex problems. So what does this mean, right? So we need that robust understanding. So students know essential mathematics, right? They know everything essential that's going into our particular activities that we're doing, or those prerequisite skills that we're talking about, right? They also then can apply those in a variety of different ways, right? Real world problems. It's not, a lot of times we kind of get stuck in a specific program that we're using, and then we realize on something like a summative or on a different type of assessment that students aren't able to then apply their understanding to that particular assessment system. So we want to make sure that even though we are following a program and using it as a guide, that we are giving them a variety of problems and really novel situations for them to be able to solve problems. And then the last part is talking about students being able to communicate their strategies and their solutions and using mathematical explanations and justifications to do that.
And then one of the things that's important is, are we using asset or deficit-based language? Sometimes just the words we choose can make a student feel like, oh, I'm not good at this, I can't do this. Or how you word something can say, okay, I didn't get it this time, but I can do it now if I just practice. So I know most of us are familiar with Carol Dweck's work and the power of the word yet, but also sometimes thinking other things. So letting a student, one of the words I used within the last year was the word but. So if I tell a student, look at, you really have this down, you got this and this, but now you're not getting this. So this is what we're going to work on yet. Just that word but kind of makes them in their mind discount all the good you've shown them that they've done and all the understanding they have. So sometimes just changing from that deficit focus, but you didn't get this, to look at everything you've got. Now we're going to be working on this. So that helps them to hold on to what they do understand and then can pull on, but they also know what they're going to be working on next or where they need to work on more. And assessments are important, and assessments have different purposes. So most of what we're going to use in our classroom are our own formative and summative assessments. And we want to make sure that we're using our assessments as helping us understand what the student knows and looking at their work so we can determine how we can better help them in their learning, and not just for sorting or reporting student progress. So do all assessments in their data serve the same purpose? So I like this cartoon. If it is tempting, if the only tool you have is a hammer, is to treat everything as if it were a nail. Well, using our formative and our summative assessments that we're doing directly with our classroom, and we see over time what's happening, really helps us to get to know our students, their thinking, where they're being tripped up on in their understandings, what they're really grasping really well. So those are the assessments we're going to use the most. Assessments like our spring state assessment, or things like the NAEP assessments, or our benchmark assessments that we only give 2 or 3 times a year, they help pinpoint where students are at one point in time. And they also help us think a little bit more about our curriculum and how we're presenting the material and the learning to the students, but they don't help us necessarily as much in working directly with the students and really knowing what their understandings and misunderstandings are that our formative and summative assessments can give us. So lack of evidence is not evidence of lack. So if I don't have evidence that a student isn't getting something, that doesn't mean they don't know how to do it. So we want to make a case for understanding what our students are understanding. So we want to use our assessments as advocacy rather than judgment on our students. We want to think about their engagement in agency. We want to think about equity and opportunity in what we're giving. Are we allowing our students multiple pathways in answering a question so that we can truly grasp how they're thinking, what maybe they're misunderstanding. And we want to get them thinking about making connections as well as us making about connections on how we can open up what we're giving them to so that they can access the learning.
Okay, so we're talking a little bit here about differentiation. Like I said, we have a whole webinar coming up for math differentiation, another one coming up for ELA, but we would be remiss today to not talk a little bit about differentiation, obviously, with our classrooms and even these types of problems, right? So we know a lot about differentiation. It's not a new concept, but what we really want to stress is that differentiation is really just about providing students the opportunities they need to be able to reach their full potential and to become mathematically proficient, independent learners. The big words here and the big things to really be thinking about are those high standards, right? We want to keep those standards high, and we know where kids are coming in, but we're not going to change what the end goal is. We're going to do everything we can to be able to make it so that they can meet that end goal. And that's what differentiation is. The other portion of this that's been very difficult in recent years is this idea of independent learners, right? We want students to be independent, yet we know sort of the reality right now is that those particular students are not quite as independent as we would hope for them to be. A lot of reasons are going into this. A lot is happening at home, a lot is happening in society, a lot is happening in our classrooms where we are not necessarily realizing just how much we are helping students. It's the walking around the desks, and as students are doing problems, pointing to it and going, look up there, or oh, try again, even before they finish. So we want to make sure that anything that we're doing in the classroom is really going to foster that independent understanding and being able to share their thoughts and with others, and really thinking about it is going to be just game changers for these kids. So the general principles also of differentiation is you need to know your students. The best way to differentiate is to know your students. You need to know what their interests are. You need to know how they like to learn. You need to know their preferences for maybe where they would like to sit, the types of people that they are working well with. All of those things, really feed into how you're able to differentiate. The other part of it is the curriculum, right? If you focus on problem solving, making connections, and having students communicate, you are differentiating in your classroom. Those are the easy ways to do it. It's not necessarily I just created 4 different activities because I have 4 different levels of students in my class and we have to do it 4 different ways. It's really just making what you have appropriately challenging and engaging for students and scaffold where you need to. So with problem solving comes flexible thinking, right? We need to be flexible about the way we're solving problems. Everybody has had the student in their classroom that the only way that they will solve a problem in 2nd or 3rd grade is with a traditional algorithm. And that's because their parents taught them that way. That's the way they know it. If you ask them about their thinking, they say, I just know. So we can't accept that. You just can't, because what will happen is that student in 3rd or 4th grade, and even 1st, 2nd, and 3rd grade that are saying, I just know, and we're not actually trying to really pull out of them the strategies that they're using. As soon as they start getting into concepts that they can't use or don't look, the way that they're used to it looking, or that they might need to have a little bit more rigor to be able to solve, they will shut down. So we want to have that flexible thinking. We want them to be able to really understand the math and to really learn it, not just apply it. And so the problem solving and the flexibility that they have in the ways that they are solving problems is going to be is crucial. This is where Annie and I were talking about who's doing what slides, and this is my slide because I get up on my soapbox just a little bit about the drill versus practice. The skill in drill method of trying to have students understand their facts is really not working. It is not, they don't understand the thinking. We're trying to have them memorize it because we want them to be efficient. And if they're not efficient, what do? We have time tests and all of that because we need that sort of understanding and fluency. And yes, you do. Just like Annie said, you need to have math fluency. Students need to understand their facts, but they also need to understand what the connection is. Addition and subtraction. How are they related? How can I use addition to be able to figure out my subtraction problems? How can I use multiplication and division together? I need to have those conceptual ideas and alternate and flexible thinking about things to be able to then be efficient and truly understand what I'm doing. Right. So we want to make sure that we are sending that message that math is about figuring things out and not about memorization. So this last bit here is really just start thinking also, especially for you K-5 teachers, because you teach everything in your classrooms for the most part. Some fifth grade teachers are self-contained and just teach math or ELA or what have you. But applying those math concepts across content areas will only strengthen their understanding and those skills that they're learning in math. So those math practice standards that I talked about in the beginning of this, that, perseverance, reasoning, problem solving, those are real world things that they can apply into any area of their academics. It's also talking about this mental discipline, right? That rigor, like that grit that kids have, and to be able to reason logically and really understanding other subjects like science, social studies, music, art, right? We have those mathematical concepts that cross over into those particular areas just within the problem solving itself, and specifically with science, engineering, and economics.
Another way we can think about how we implement problem solving in the classroom is through small groups. So groups can be formed on pedagogy, that the teacher says, okay, I'm going to create homogeneous groups, or I'm going to create heterogeneous groups. I'm going to have somebody who really gets it, somebody who's really struggling, and a student in between, and put them in a group so that they can support each other. Productivity, a teacher, you can arrange the groups on who can complete a little more work, and they, will give them the role of leader of the group. Or peacefulness. Sometimes we just need to create a group just to have that peacefulness, keep students who are fighting that day not going to be in the same group. Or we can use social goals. We want diversity, we want inclusion, we want that social aspect coming in. So there are lots of different ways we can create our small groups. Another perspective is from Peter Lilladell, and he's saying just random grouping. And this is something that's not new to us. I've seen plenty of teachers, you're pulling the popsicle stick out of the jar with the students' names and say, these three are in this group. You're having them pick cards, you're drawing names from a bucket. So random grouping, and the important thing with that is the students know it's random. They know that you didn't secretly put them in there, that it is truly random, pulling out the names. And from grade 3 and up, Peter Lilladell said, groups of 3 are really good, but for K-2, we only want groups of 2 because they're still practicing some of those school skills. It takes time to implement, and we know that anything that we try to do takes time to implement. We're learning to do it as much as our students are learning to use it. So, but some of the benefits of having small groups within the classroom at times are the willingness to collaborate. It can help eliminate some social barriers sometimes, knowledge of mobility, especially if they're not always working with the same people, increased enthusiasm for math learning because they get to learn with somebody else. It's not all on them. And it can reduce social stress a lot of times. So visibly random groups for grades 3 and up, 3 students seems to provide the best balance for redundancy and diversity. If I can't make all groups of 3, it's preferable to have 2 groups of 2 rather than groups of 3 and then 1 group of 4. And then K-2 students, because they're still learning those early social skills, the group of 2 student allows for that parallel play and allows them to move from turn taking to discussion. My turn to listen, their turn to talk. My turn to talk, their turn to listen. So it works because it gives that increased willingness to collaborate, and that can take up to 3 weeks to do. It's not always a quick, they'll do it and they'll like it. Elimination of social barriers, increased knowledge, mobility, that if I'm talking over the course of the week, if I'm in 2 or 3 different groups, I'm gaining that much more knowledge because I'm talking to that many more people. Increased enthusiasm for mathematics learning and reduced social stress. And this, you will get a copy of the slides later on, but this chart gives you an idea of, here are some talk moves you can use for supporting the classroom discussions, because we learn through talking. That's one of the ways we learn, and we want to facilitate those discussions in the students so that they're exposed to other ways of thinking, ways to approach a problem. You as a teacher really get to know them and what are their understandings and how are they approaching things. So this chart gives an idea. Here's the talk move, what it means, and then some examples. And there are types of questionings, and we use all the types of questionings in our classroom, but we want to be aware of what type and what it may give. So funnel questions are designed when I really need to pinpoint a student to one thing. I may lead them down one pathway so narrowly that they'll come up with what I want them to come up with, and then we can expand from that. Whereas the focus questions will give them ideas and parameters, but they may take multiple pathways, and they have to use their thinking a little bit more, as well as really pulling on what they know and then applying it to get to where they need to be. And then we have explicit and guided questioning. So explicit, telling exactly how to do a procedure or a process. Sometimes that is the approach that needs to be done, but it's not what we want to use all the time. And on the other side, we're also giving them guided questions, which goes along with the focus questions. We want them to pull on what they know. We're giving them the ideas of what are past things that you know about to think about, and they're making the connections and arriving at the answer. And then the types of questioning, funneling versus focusing. John Hattie was the one who I think really brought it to the forefront of people's knowledge. And this just gives some examples of, here, what are some funneling questions? And then if I want to open up the question more and get the student thinking a little bit more, here are some examples of some focusing questions. So instead of how do you find the mean of the data, to what do you notice about the data? How would you describe it to someone? So it opens up the question. They have to be a little more observant and pulling in a little more of that noticing and wondering routine. And we often forget that writing is part of conversations and discussions within the classroom. So writing is a conversation with reading and a dialogue with thinking. So writing helps students to compose and get thoughts down before they start talking with other people or within the whole class discussion. It's getting them to think and play around with what they're doing, as well as it helps them to improve what they're doing. So to write is to think. So if I'm going from here and what's the next step I need, and then thinking, and they can play around with the different things. So writing, and also starting to write about, think about the audience and purpose that you're writing to. Can I get things down, and then I can discuss with what I'm doing with a partner, and then we can share what we have and create a whole class discussion. So it really helps build that learning, but it helps students think about what they know themselves first. Classroom discourse includes both oral and written language. So writing plays a critical role. Again, it serves as that rehearsal for discussions. It also allows students to use it as a reference, so they can go back and look at things. And remember, writing, especially in mathematics, can include diagrams, pictures, tables, graphs, pictures that help them remember things. So writing also helps to develop and show a need for precise language in mathematics. We want to develop that academic language. We want them to learn to say vertex instead of corner when we're talking about shapes. And illustrations can support and make a good example. So having that word wall can really help students see things, especially if they're creating the pictures to go with the words up themselves. Seeing various strategies and solutions is like hearing about the solutions. So they're not just seeing what they're doing, they're also seeing how other students approach things. And then they're able to talk about why they use the strategy. So they get that greater depth of understanding that they're building within their own selves. And then they might be willing to take a risk on, let me try this approach because my approach isn't working, but I remember so-and-so doing this. And a written product can help one further analyze student understandings. So when you take a look at math journals, at how they solve problems, you gain you gain a better understanding of how is my student approaching this problem? What is it they're really understanding, and what connections are they making? Oh, they got off on this misunderstanding, but I can see why they misunderstood this. I can see what they're thinking about. So now I know how I can better help them. Graphic organizers and foldables are a great way to support writing in the classroom. They can use to help students summarize what you've talked about. They can be used within note-taking systems to help remember things and make and connect ideas. I've known people who have had interactive notebooks that really help students. So there's a way large range. You can bring in graphic organizers and foldables to support the writing and the thinking, and then support the vocal discussions in the classroom.
Great. We've had a lot of people in the Q&A saying they're sorry they had to go off. We are finished up with pretty much the content for today. It did go a little bit long. We appreciate you folks staying on. If you have any other questions, definitely let us know. I just wanted to pop up here. We have 3 webinars coming up: iPlatform and the website for the New Hampshire Department of Education, and all the data and everything up there is ready to go. So we have an iPlatform webinar coming up next week. We also have coming up in February and March, best practices for math differentiation and for ELA differentiation. So keep an eye out for emails that will be coming out for those if you're interested in differentiation. And again, we would love your feedback. We know this one went long. Hopefully the information was really valuable for you. And you will be getting an email tomorrow recording, slides, and a couple other supplemental materials, along with probably another link to the survey that will pop up as soon as I close this. And I just wanted to get to our email addresses so that if you have any other additional questions that maybe weren't getting answered during this webinar, we would be able to answer them for you. So
yes, and please feel free to reach out. Remember, both Heather and I are resources for you. So it's never ever a problem if you reach out. That how can we help support you in the work that you're doing?
Absolutely. So I'm just checking the Q&A. I think for the most part, there aren't any questions here. So have a great afternoon and enjoy everybody.